Rotating chairs. Everyone at some point has sat and unsuccessfully resisted the urge to spin around in one. It's so much fun. When you extend your arms and legs, you rotate slower. Bringing them in makes you spin faster. But how does this work, in terms of science? We did all the nitty-gritty math and calculations, so you don't have to.
Before we calculate the momentum of spinning chairs, here are some constant measurements. First, we measured the diameter of the base of the chair to be 2 feet, resulting in circumference to be 6.28 feet, and multiplying this by 3, the number of full revolutions made, we get the total distance traveled to equal 18.84 feet. In addition, we estimated the average weight between the two of us to be 75 kilograms.
For this experiment, we assumed every part of our body was moving at the same speed to avoid complications and because our data was not 100% exact.
Let's test spinning with our arms and legs extended outward. We timed how long it took to make 3 full revolutions and repeated this 5 times, averaging the number of seconds together. For our first example, we averaged 9.08 seconds to make the 3 revolutions. Divide the distance of 18.84 feet by this, and our velocity is 2.07 feet per second.
Now we will test with our arms and legs pressed against us. Using the same methods from earlier, we averaged a notably lower 6.52 seconds, and when we divide our rotating distance by this, we get a velocity of 2.89 feet per second.
We tried to spin ourselves and push off just as hard, and we see here that you get a greater angular velocity with your arms tucked in.
Now we can calculate momentum by taking the equation momentum is equal to mass times velocity. P equals m times v. All we have to do is plug in the numbers, let the calculator do its thing, and boom.
With hands and feet out, our average mass, 75 kilograms, times 0.63 meters per second results in 47.25 newtons. Okay, whatever. But, with our hands and feet brought inward, average mass times 0.88 meters per second equals 66 newtons. That is a 39.6% increase in momentum. Wow!
Our conclusion? You go faster with your bodily limbs up against you. We solved a pointless observation for science.